Scientist and physicist and computer scientist by training. And let's get this presentation showing. Hopefully I can get into the slideshow mode. And like Susan said, there's a team of people, part of our project, who are here, Bob Sinkovitz, Nicole Walter, Marty Candace, and they'll answer your questions in the chat. And then Bob, if you could play Cindy for me, in the sense of let me know if there's so many questions we need to pause. We made these webinars a little bit longer than usual to make sure we have plenty of time to answer questions in the topic that we're addressing, or to make sure we're keeping up with the chat. So just let me know, Bob. And I do have an outline for the talk, and when I get to each different section, I'll stop and also see if we're on track, or there's any late important questions. So about the complex project, it's an idea that Bob Sinkovitz came up with, about the realization that there's a whole crew of people who use HPC and cyber infrastructure resources who aren't programmers, from the concept of a programmer who goes in and writes code and develops an MPI code that's going to run at scale on a supercomputer. And so we our focus on this project then is on people who are going to come in and use the system, but that's challenging in and of itself. So we want to help address and train people and provide information on that scale. So the topics in the program will include parallel computing concepts, Linux tools, bash scripting, security, batch computing. We'll cover a broad range of topics that don't require any programming, but they still require the skills needed to operate within a high-performance computing infrastructure. This project is funded by the NSF. And so with that, I'll start out with an introduction overview. So this session is on Linux environments for people who want more skills in that area. And as we say in here, in the Linux world, or Unix, you'll hear that used interchangeably, intermediate is in the eye of the beholder. So things that we're going to cover in this presentation and other topics down the road might be considered beginner in the eyes of a sysadmin, but most of our users who come in to do science are not sysadmin types. So we're trying to meet you on the level that you're at in trying to get things done. You still need to know a lot of Linux, and if you're new to it, it can be very challenging. And so we have some links to related beginner material. If you're attending this session, you're probably not a sysadmin. So we'll keep these topics at this intermediate level from the perspective of users doing science on parallel computers. So we assume that you already know Linux basics, such as listing files, removing files, navigating through directories, looking at what's inside a file, and you can do editing on the Unix command line, which is challenging, and that you know about paths. If you need to learn a bit more, we have a basic skills tutorial, and we'll put that link into the chat. And also the Supercomputing Club is a bunch of students at UCSD that we sponsor. They came up with their own insight in their own tutorial for Linux computing, and it's kind of fun if you want to go see it. Or just do a Google search. There's a lot of tutorials out there to help you learn the very, very basics and get started. The one that I've put in here for Linux skills on Expanse, it's specifically everything runs on Expanse. So if you're working on Expanse, and many of you are, but not all of you, one of the things we're trying to do in this complex program is to make the tutorial material, the training material, machine agnostic, so you really can try everything on many different systems. So let's talk about file systems. That's one of the more confusing parts of working on a supercomputer, is file systems. And so for Linux, there's the File System Hierarchy Standard, or FHS. It describes the conventional layout of a Linux system, and that they're slightly different depending on who's administering the system and what kind of Linux they're using, the flavor. And they tend to be pretty minor, the differences, but they are related to where information is stored. So typically you'll see /lib, and so if you're familiar with Linux, the slash means root. That's the highest level, /lib/bin. The slash sign is used to separate directories or folders. If you're used to Windows, that would be a backslash. But we have a /userlib, /userbin directories. Those are pretty much going to be universally available. And then files might be put into something slightly different depending on the kind of system you're working on. So you don't need to know too much about that. Administrators put the software in there for you to use. It's just helpful to know that those are out there if you're trying to find some tool that you need. And then if you want, there are some links posted on this slide where you can go to Wikipedia, the Linux Journal, and other places with more information about Linux tools. So what you're going to be seeing is /home. That's where your user directory might be located on a typical system. It could be called something different depending on the cluster that you're on. You're going to have a /bin, a /userbin. That's typically where you have commands that you're going to be using, like ls, pwe, cd, changing directories. Then there's sbin and /user sbin. These are mostly used by sysadmins. In general, sometimes these are merged or cross-linked. And then there's libraries that are needed by the Linux commands or some of the software that you might be running or developing. And then /opt is it's a place where software gets installed traditionally for larger application programs, but now there's package managers like SPAC, so it's not /opt is not always used. Especially on supercomputers, SPAC is a very popular software for installing and managing all the applications. In addition, there's /etc, which has configuration files. /root is the home directory for the root user. Typically, only sysadmin people can look at the contents. You might not even be allowed to look. The /var is where log files go for web pages and log files generated by applications you might be using. You are allowed some visibility into the log files. /dev is device files. /proc and /sys are pseudo file systems, and they contain information about running processes and hardware. /temp stores temporary files. You can use /temp, but your files are not guaranteed to stay for very long. Not everything fits into the FHS, especially on HPC systems. So you'll be seeing some of the software that you use in different file locations. For Lustre, which is the name of the large data storage system on Expanse, for example, that lives under Expanse Lustre projects and Expanse Lustre Scratch. Projects and Scratch are a little bit different. Projects is where you might have a folder or a directory and it will be guaranteed to remain. Scratch is on HPC systems and it's not guaranteed to hold storage persistently, so don't keep good data on Scratch. We'll talk about that in another tutorial down the road. Cumulo is mounted on Expanse, that's Expanse projects, that's cloud storage. And other software using SPAC package manager are found under on Expanse /cm shared apps SPAC. And you'll get to know /cm shared as you work on a system like Expanse. So symbolic links and hard links. This is a tricky bit that we consider intermediate for the level that we're working at. They give you a way to refer to a file or an inode, which is a file data structure, information structure. You can refer to it by a different name, and they're helpful when you're writing or installing software where there's the relative path stays the same even if you put in some software with a different path. So if I always want to have a link to my application, but I have different versions, the my application link will always be there, but it might point to a different version. And we'll discuss the difference between symbolic links along in the next few slides. So links are created with the ln command. So this example shows a soft link for file 1 and soft file 1. And a hard link is, and we'll talk about this in a moment, hard file 2 and hard file 2. So the inode, let's talk about that really quickly. It's a data structure that stores information about a file system object. In Unix, everything is a file. An application, a folder, it's all got information, but it's viewed as a file that can be handled by applications. So it's going to have information on permissions, who can use it, file size, ownership, timestamps, location of data, but not the actual data. So the file is a link to an inode, and a hard link is just another file that links to the same inode. An inode's only deleted when all the links to it have been deleted. If the original file is deleted, the data can still be accessed using the hard link. If you have a soft link and delete the original file, the soft link doesn't work anymore. So here's an example. I want to point out that in this talk, for every slide that has an example on it, we have that test scripts that will help you work these on, use these examples. So that's in our GitHub repository. We've posted the link in the chat, and hopefully somebody can keep reposting that for people who arrive later. But we have a GitHub repository, and we'll give you a link to that, and you can find examples of all these slides. So in this one, we look and see and do a file listing and see that there's file 1 and file 2 present. We make a soft link of file 1-hard to point back to file 1. Then we'll make a soft link, excuse me, that was a hard link, pointing file 2-soft points back to file 2. So ls-il, the I option lists the inodes, shows you that file 1 and file 1 hard have the same inode. File 2 and file 2 soft point to different inodes. If you remove the two files and try to print out the contents, remember cat is to print out file contents. File 1 hard, it has contents in it, but for file 2 soft, it's gone because we removed the inode got removed to file 2. You think, why do I need to worry about this? Well, you want to know where your files are and are they still around and can you still access them? So link ln file 3 to file 3 hard, but there is no file 3, so you can't make that. And ln-s file 3 soft allows you to try and do it, but you still aren't going to have any information. So here we look at a file that is in expanse, lesser scratch, syncobit, file 4, and file 4 hard. So we make a hard link back to this file that exists, and this file 4 hard will be in the directory you're currently in. But it couldn't create that hard link because it's invalid cross-device link. So this is what happens when you're on two different storage devices. It does allow you to make a soft link though. So you have to be careful. Am I on my home directory, which is one storage device? Am I on the directory of a node on the cluster that you're working on? Am I using Scratch? Am I on the projects directory? Those are different devices. And that's where the complexity of files becomes a challenge if you're moving files around, and we all do when you run jobs on the compute nodes on a cluster. So learning where your files are stored and how you can access them is important. So redirection and pipes. Let's look at that. So redirection and pipes. So since everything in Linux is a file, you can look at the contents of the file, even the inode information about the file. And most of the commands write to something called standard out. If you're a computer programmer, you know that there's standard in, which is when I type in the command line, I'm putting input into a running process, and there's standard out and there's standard error. And typically those all show up on the terminal screen. These are a terminal that we've launched and we've logged onto a machine like Expanse. And so I'm going to run a command called the date. And the date would normally just print out the date, but I'm going to redirect using this right caret to a file called out file. And then if I look at the contents of the out file, you see there's the date. So commands can be run so that the standard out goes to the command line, the terminal, or you can store it in a file. And this is a really powerful way to work with your data and organize your data and track what you're doing. So the date goes to out file, and I look at the out file, and it will, if I do it with just one caret, it will overwrite the contents. But if I do a double carets, this is an append command. Now if I run the date and I append it to the existing out file, you'll see I have two different dates. So that's a very powerful command. The second command for redirecting output is called the pipe, and it's really a fun command. I use it all day long. It takes the standard out from one command and directs it to the standard in of a second command. So you can make a whole chain of commands as you're like trying to go through a directory with 1,000 data files and you want to see if any of them have a certain piece of information. You could filter and you can just keep piping these commands together to get the information that you need. So we want to count the number of files in the current directory in this example. ls-l, ls-1, and pipe the output from doing a file listing into another command called word count. And we find out there are 13 files. So here lists the 3 longest running jobs on Expanse node, number 20, Expanse 209. So you run a command called sq, and you'll learn about that in our tutorial on running jobs. But sq tells you what jobs are running on the Expanse cluster. I'm going to use a command called grep, which is a filter command, and look for jobs on this particular node, pipe it into head. And so remember, the listing of the jobs on the queue goes into be filtered using the grep command, which is a big list of jobs, and then just look at the top 3. And so out comes the information here. So once you get the idea of piping the output from one command into another one, and then into a third one, for example, it's really quite fun, and it's very powerful. So redirection and pipes, you're looking at standard in, that can also be redirected. Normally you use the command line, but you can, for example, have it read a file. Here we're using word count, and it's saying look at the contents of file 1.txt, and it will tell you that there's 9 lines in file 1.txt. Or I could look at file 1, pipe that into something called cut, and just look for the line count, and I come back and I get 9. And then here, this could be another way of just looking at the number of lines. You could look at the number of words depending on how you use this cut command. All right, wildcards and globbing. Make sure we're doing on time. Well, I'm going through this quickly because we have a lot to cover, but you can, I guarantee you can run everything here on probably your home system on Expanse, and you can find every one of these commands out on the web. You just have to Google it, and you can get more information on each one of the commands that we're covering. But wildcards and globbing. So wildcards allow you to do pattern matching, which is something that is quite popular on Unix machines. So you can use combinations. Question mark will match any character. Star will match any string, including the empty one. And left bracket matches multiple characters or ranges of characters. So if you think in terms of the characters in file names or the characters that are in the contents of a file, you could be looking and searching in that file for particular strings or characters. So globbing is the operation that expands that pattern into a list of files. It's done automatically by many Linux utilities that operate on files such as ls, remove, move, cat, head, tail, and file. So wildcards and globbing. Let's look at the command called ls. I'm in a directory, and this directory has a lot of files in it, obviously, and the ls command by default will list every single file and give you the names of the files. It doesn't give you any other information, just the names, but there's a lot of them. And here I want to look at ls, that's this first command here. ls file star says, give me all file names that begin with file and can be any other characters afterwards. And so here it didn't get cxefg.exe, that doesn't contain file, but it did get all of these file names that begin with file. And anything beginning with an F, now it does capture some of these other file names. So I'm using this wildcard to look for particular strings or substrings. In this example, I'm looking for anything with GHI, star, GHI star, and it indeed found 3 of them. And you can use this wildcard to even look inside a file to look for strings inside the file using the grep command. So here we're using the question mark now. So we have our listing of files, and now we're going to look for a character after file. In this example, file, any character, but it ends with .dat. And we found several files that indeed have any character, file question mark, and then end with .dat. Here we're using LSA star CDE dot star, so that's A plus any character plus CDE dot plus any string. And so we got 2 files for that. And then this is any 5 characters, any file plus with a dot, and any character plus X, and any character after that. And it found conditions, file names that matched these conditions. So you do a little bit of playing around with that. It can be quite handy. And here we're using the left bracket dot 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 right bracket globbing. So again, here's our list of files. Now here, multiple matches using lists of integers, and came out with 1 and 3. Any multiple matches using a range, file 1 through 3, we found file 1, file 2, file 3. And now any letters, any files beginning with A or C with an X, and then anything after it. And so we found 2 files with that. And then any file beginning with A through C with an X and any ending after the X, and 3 files were found. So being able to do wildcards and globbing is very powerful. And again, you can also apply those to contents of the file using commands like grep, awk, and sed. Let's talk about aliases. So aliases are great. I live by using aliases. They're really good for shortening commands that you use a lot and you get tired of typing them out. So be careful though. First of all, there's a little bit of a warning here, which is alias remove, so that every time you try to remove, you get asked, do you really want to do that? So you can remove, you can alias to write to /temp. There's a classic beginner Linux user who deleted everything in their folders because they didn't alias remove. And so at the beginning, I especially recommend that you use alias. You can abbreviate a long command. Partitions, in this example, alias partitions gives you some information on and particular output that you want, and the formatting of the output from the partitions command. And so if you want to know what aliases you have, you can say which partitions, and it explains the alias. Whoops, sorry about that. And then here I'm going to alias. I use this one a lot. My favorite one is to do a more expansive information about the files. So the ls-al, and in basic Linux, so you know these arguments, you can tell the file permissions. You get an idea of who owns it, the group they're in, the size, and the last date it was worked on. So that's a useful command that, for me, I like to see what kinds of files do I have. Are they a directory? So I use ll a lot. Aliasing, you can find out how many aliases. You might inherit a few aliases from the operating system. From sysadmins, they've created them when you first log on. So if you type the alias command, then you can see the ones that you've got. In this example, we've got partitions, reservations, spactivate, so turn on the spec environment. You can do whatever you want. You can make all kinds of aliases. And you can also put them into your bash startup files to pick up these aliases every time you want to use them. So command history is pretty important. Again, I use it all the time because you can look back and see what you did, and that's stored by if you're in bash, it would be under bash history. You can see what you've done in the past you can tell it to keep track of my commands out to 1,000 commands. And so here, snip is a typical word used, by the way, to show that the output from history was really, really, really long, and I cut out all that just to keep the information I'm showing you. So here, ls file star, I did a listing, I removed a file, and I printed out hello. And then if you want to execute the last command that you used, use the exclamation point, ls, and that will recall that one command and execute it for you. Or you could also say redo exclamation 430 would echo hello 2 commands ago, or you tell it exactly execute that command. Very handy when you're doing development, testing and retesting, and you can recall those commands and you don't have to type them out again. You can also pipe those commands into each other. So navigating between directories with push and pop. So navigating is pretty challenging. You need to know where you are. A lot of times you have subfolders with data in one folder and executables in another, and moving around, you want to be able to do that. Typically, it's not unusual for somebody running a lot of jobs on their laptop or on an HPC system to have multiple windows open as well, terminal windows. But if you're staying within one, you can do push D and pop D, and the system will remember where you came from and where you want to go. They allow you to move. Push D adds directories to the stack. There's a stack of directories, and pop D removes them from the stack, and DIRs will list the current content of the stash. So here we're going to push a directory called push D dir1 and push D dir2. So it prints out the name, the contents that are now in the stack. And we're going to push a couple more. And then DIRs, you can see that we have multiple directories in that list. And then you can pop D and off we remove this directory from the stack. Okay. Environment variables. Shell and environment variables they're pretty important. They're what the system keeps track of while you're logged in for you. The system has a lot of shell and environment variables of its own, but when you log in, Bob, I see a lot of questions in the chat. Am I going too fast?
No, not at all, Mary. We've got them all covered.
Okay, great. Shell and environment variables, let me go back to this. They're only known within the current shell. When you log in and you're on a terminal and you log on to Expanse, for example, you're in a shell of some kind of environment which allows you to run commands. The environment knows who you are, and when you launch an application, you might go into a different shell. But the shell is the current shell that you're in is the one that you're interacting with. And there'll be variables associated with that, what directory you're in, who you are, what colors you like to have for particular commands are in there. Links to path links to where commands are located, like in /user/local/bin. It has a lot of information in there, and you can make your own shell environment variables as well. And when you go to a new application or open up another terminal, you'll get a different shell in that terminal as well, that other environment. Environment variables, so shell variables are only known within your current shell. Environment variables are known globally and are inherited by processes and shells that are launched by the current shell. More often than not, you probably want to use environment variables rather than shell. And this is a really important thing and to understand is what variables do I have available, and when you're writing a script to run, what variables go into that script, and when you launch a batch job, which is a script, what variables are in the batch script that you write to run a job on the parallel computer. The environment variables are really important, so learning to play around with them, creating them, like when I'm copying a lot of files from one directory into a directory I'm in, I usually define that path to that remote directory explicitly as a shell variable, and then I use it so I don't have to type out that long directory. There's a lot of conditions where you might make a shell variable that you're just using right now, but environment variables, no matter where you are or what you're running, those are known globally and inherited by the processes that you launch. So the variables are set using key equals value, and you can have a list of values for that key. Space is not allowed around the equal sign, and by convention the key is capitalized. Doesn't have to be, but by convention. That way you know you're using a shell variable. They're made into environment variables using the export command. This is when you're in the bash shell on Unix. If you're in a different shell, it might be a little bit different how you export these environment variables. Just a little caveat there. You can look at the value of a shell or environment variable using the $key. So here we're going to build a couple of shell variables, key 1, key 2, and we're going to export these to become environment variables. And we're going to define key 3 to be an environment variable. We can echo $key1 and see that it's ABCD, which it should be, $key2 and see that it's EFGH, and $key3. So echo allows me to print out the values of these shell variables. The $sign allows me to access the value of that variable. So if I launch a new shell /bin bash, again, there's Z shell, T shell, C shell. Popular ones are bash shell and Z shell. But now I'm actually in a new shell. It's as if I've logged into a new part of the computer. And they're echo key 1. It allows me, but there's nothing in it because key 1 was only known in this parent shell up here. And key 2 was inherited because we exported the value of key 2, and as was key 3, which was exported as well. So this sort of gives you this hands-on view of how shell variables work. Another way to assign the variables is with the declare command, using the -x flag to export. So you can declare var1 equals ABC and declare and export that var2 equals DEF. And this might be if you're on a system where they don't have the export command. Usually that's everywhere, but you can use declare. And you can make it read-only within the current shell, -r. So echo the variable ABC, echo var2, DEF, bash launches a new shell, and var1 is only known by the child shell, and value var2 is exported, so we get the def. We have a value for $var2. Sorry about that. Okay, so in the shell you have these environment variables, and you can see every variable shell and environment by running the command called env. And it can be, if you have a lot going on and you've installed a lot of software and you're on a big system like an HPC system, this can be 100 lines long, especially if you're doing a lot of work on and you've loaded a lot of software into your environment. But this is a pretty simple one. The path, and if you see like cm shared apps SDSC 1.0 bin : this is one path, and the second path is sbin. The third path in your environment is cmshare apps slurm current sbin, and it goes on. There's user bin, there's user local sbin. So it's a concatenation and then of different locations where you can find Unix commands. Like ls and cd are going to be in probably user bin. But also we have a home directory for a user named syncofit, anaconda bin. This means as you try to run commands, your shell environment will look for commands starting at the beginning of your path and go until it finds the first occurrence of the command you want to run. This is a little tricky. So if there's a command that's normally in user local bin, but you've made your own version of it, it won't get found. It would get found up here. So you have to be careful how you're ordering your path. And so it's really smart to not make a command that's the same as an already existing command. But that can happen sometimes and cause some trouble. So the path is important. As you add new capabilities into your environment, like a new library that you want to have, a new application that you want to be able to access, make sure you have to add that into your path. And we'll talk about where that is done in this talk. But it goes into your bash RC type of startup files. Here's a manual path. Most Unix commands and most applications that are developed, they have a manual. And so you could type the man and the name of the command, and up will come up, and some information on that command should come up. And not always, but sometimes you want to put in a hard-coded path to where the man pages are located. You'll inherit that when you log on to a big system. Your login name, here's syncofit, and what shell user syncofit wants to use is the bash shell, and the location of the home directory. This is typically built for you by the system admins, and there's a slew of other information that will show up when you look at environment variables. And if you created one, it would show up, like all the ones we created in the previous examples. If you typed out env after you did these examples of creating environment variables, they would show up on this command as well. And so you can, if you're looking for a particular variable, you would run the environment variable and then use something like grep and search for a particular variable to make sure you've got it. Oh, and every time you launch an application or you go into a new shell, your environment will change. So sometimes when you're trying to debug when things go wrong, write a little, like you're submitting a batch job and something's not working, run the environment command inside your batch job to see what variables are being inherited by my application on that computer node on the HPC system on that day and when my job got launched. And you might find that you're missing an environment variable or it's not set correctly. So the next thing are these configuration files. I've loosely referred to them. The configuration files are what we use to get things going. The .bashrc, the .bash_profile, typically they do begin with a dot. And dots are called hidden files, and you won't see them if you just type ls. You'll see them if you do ls-al, my little ll command I showed you earlier. It would reveal hidden files. And a lot of applications create hidden files. You might think you have 10 files in your home directory, but if you do the ls-al to show everything, you'll find you have 10 or 15 hidden files that different applications that you use are creating. So you want to be aware for lots of reasons, from it, and mainly, from a security, primarily from a security perspective. Make sure you know every file created in there was something that you wanted to be in there. And if not, send a note to consulting and ask them if that file's okay. But also you want to know what applications are creating these files and what data is in them, because you might need it for general information for debugging what your software is doing. So knowing about these files are important. So for the bash RC and the bash profile, these get executed when you first log in. The first thing that gets launched is your your bash RC, and then it launches the bash profile. And these are generated from master files, etc profile and etc bash RC. You can look at those contents, you can't change them, but every user inherits what's configured in there by the system administrators. They set that up so we all start with a uniform environment. Then you customize your local environment by modifying the bash profile and the .bash RC. And so there's a hierarchy of scripts and source scripts and other scripts that apply to login, and other scripts that apply to the applications you're working with, and it can get a little messy. So learning to manipulate it is fine. If you screw things up, talk to the consultants. They'll help you restore your bash profile. But you need to learn to control your environment, understand your environment, and modify your environment. Once you get the hang of it, it's pretty straightforward. So you can get these two general rules. Customize your environment variables in your .bash underscore profile. Like that's where I would put my aliases, for example. Or in here, you can put them in the .bash RC. But environment variables in bash profile, aliases and functions in .bash RC. Sorry, I misspoke. That will generally help you know where to go to look for things, especially when things don't work. Where did I put that one alias? Where did I define that environment variable? All right, so what are the differences in interactive, login, and non-login and non-interactive shells? What kind of shell are you in? An interactive shell is one that reads from and writes to your terminal. If you can enter commands at the command line and see the output, you're in an interactive shell. So the interactive login shell is launched using SSH. Like when I log in from my home computer, I used SSH to get onto Expanse. So the shell is launched using SSH locally, or when a new shell is launched with the -- login option. This is where you'll usually work when you're going on to Expanse. An interactive non-login shell launched from the login shell. You get that by executing bash at the command line or opening a new terminal from the Linux desktop. So both shells, though, allow you to interact by running commands. A non-interactive shell is not associated with a terminal. It's usually launched by a user executing a script or associated with automatic processes. Like when you do learn submit a job onto like a bash, a Slurm scheduler, for example, on Expanse, it will generate and run commands for you that are not interactive. You're not interacting with them. It's all being done automatically for you by the Slurm job scheduler. So how are things executed? That's important to understand what gets launched first. So point out in this color scheme here, anything in the orange boxes, those are done by the sysadmin people, but when you log in, these get run first by the system, and then the system will look at your bash profile and your bash RC. And depending on the Linux flavor, you might have something called bash login and .profile. Again, these are the things that are a little bit different. So interactive non-login will execute .bash RC and then execute, and then that executes the etc bash RC. If you're curious about that, we have a link in here on bash startup files. So although bash RC normally sources etc bash RC, the latter contains logic to ensure that its content is not executed twice. So it depends on what you're doing. You may, the entire time you're on a HPC cluster, you may never change these. Odds are you'll change them a little bit. At one point in time, I was running and developing a lot of code, and my bash profile was, my bash RC was 150 lines long. because I was working with and testing a lot of libraries. This was before the current lovely system where you can load modules and inherit software that's been is installed and supported by the sysadmins. This was about 20 years ago. So nowadays you load in modules, and we'll talk about that in a future tutorial. The modules allow you to inherit software already installed, debugged, and tested by the sysadmin people, but you can create and only use a particular type of library, for example, that you want to use, like for OpenMP or MPI or something else. Okay, so the bad news. Linux configuration files, it's called tree-based because you start, with it's hierarchical, and you have to start somewhere with bash, and then shells get launched that might be remote or normal. You log in, you may have a non-login activity going on. It could be interactive or non-interactive. It's looks like what we used to call spaghetti code. So it's complex what can be happening, and we bring it up in this tutorial because I think you should realize that if something goes wrong, and often things go wrong, or change, and things break, you need to realize that if you're confused, there's probably a reason. Somewhere in one of these little nodes on this process graph might have broken down, and it might not be your application. You may have changed a line of code in your test script and it's now breaking. But sometimes identifying where in the software stack that you're using there's a problem can be complicated, which is why we have such a strong user support group. And when things don't work right and you can't figure out where you are on this graph, appreciate that yes, it's complicated, and yes, it's okay to send a note and ask for help. The good news, if you're using bash and you're not a sysad, you probably just need to worry about these two files and these two processes. But again, behind it is an awful lot of complexity. So these may be working fine, and there may be some other problem, and so it's important to realize that you can control what's in here. But if you have a sort of a hello world example and it's not running, and it should run because it's the simplest thing, then it's probably something over here that you're not that you're not having a problem with. There could be a system problem. So make sure these are clean, and if you haven't changed them and you haven't changed your basic code and something's breaking, it's probably all of these processes back here that you don't need to worry about. But they might not work if there's something going on with the system. Okay, so configuration files. Let's look at this configuration for bash profile. These are commands that are only run once, such as customizing environment variables and defining some aliases. So make sure in your bash profile that you have executed the .bashrc first. And this goes sequentially through. And now I'll add some locations to my default path, and these would show up like here. I'm adding the AMD profiling software into my path so I can find it. So this will always be in. Don't edit that part, please don't, because nothing will work if you don't get the default system supported .bashrc and whatever else you might have put into that .bashrc. Okay, so just make sure you're careful how you edit it. And then in the bashrc, the first thing it does is launches the etc bashrc. Notice the Unix developers allow you to not do that. That doesn't mean anything is going to work. So the .bashrc, which gets launched first from your bash profile, launches the etc, the system bashrc. And then we put in a couple of aliases. Here is a command called module load slurm, module load SDSC. We'll talk about modules. I spoke about them a moment ago. Modules are ways of loading in environments. Until I run this command, module load slurm, my environment doesn't know about the slurm batch job scheduler. But when I enter module load slurm, it will inherit and get all the environment information needed for you to run slurm commands, like that SQ command we cited earlier. Okay. Pseudo file systems. I see I need to get moving so we still have time for questions, if there are any more. Following the philosophy of everything as a file, Linux distributions provide pseudo file systems that allow you to access dynamically generated content using the same tools that you use to access a regular file. They're normally found in the /proc and /sys directories. So here, ls-l proc/proc/cpu info. There is no file size, but I can find information in there that's dynamically grabbed at the time I execute this. This is really helpful so that you know what kind of CPUs you've got on your system. Bash scripting. Well, this one can go on for a long time. You've seen lots of examples of shell scripting and bash scripting, and some of the commands that I've talked about above can actually be written into an executable script. So you can make if you write a script, script is a code that can be written in using bash syntax. And you can make it executable and then run that script. You can run, it says here ./script.shell. That depends on the system you're on. This one works here, run /. That says the dot means in this directory / run this script. And you have to make sure it's executable with that 755 read, write, execute, and this one is read and execute. Source script.shell, that will execute the script, and .script.shell. This doesn't work on Expanse. You need that /, but this might work on your local file system. Script, we'll show you a few examples of shell scripts. So at the beginning of the shell script, you want to tell the system what shell you want to use. Here we're just using the default shell, and we're going to echo a line, some text. We're going to look at a file and do the same thing for a couple of files. And when you ./simple.shell, then it would print out these lines of text. So in here, we're actively doing some commands, and then we get some output to standard out. I could redirect that to some file name that I want, and this output would go into a file. And here we're just looking through for, and we're going to iterate for all the files, thinking it back on the directory that has lots of files with file star.txt. For each file name, do something. Here we're going to do a word count, and when we're done. And then we're going to do the same thing in this block. We have 3 blocks that will get a line count with different syntaxes. And in this first one, we have 9 lines in the file that have get the line count for these files. And then all 3 versions produce the same out, assuming the directory contains files of the file123.txt format. If you need to iterate over a range of numbers, you can use one of 2 approaches, either with the sequence command or using a curly bracket notation. So here we're going to concatenate the content of all files that have a 1 or a 3 in the file name. And we're going to, here the example is concatenate the content of files 1 through 3 for I in 1.3. So this is a for loop syntax, similar to Fortran or C. Here we're going to concatenate the content of even numbered files. So this one is sequence from 10 down to 0 in steps of 2. And these examples are in the GitHub repository. Want to make sure. You can accept command line arguments. This is very powerful because you can use this for a script you're writing. You can pass command line arguments to a batch script for running jobs. So you use the $1, $2, $3, storing the first, second, third, ... arguments. So $0 stores the name of the script. And every script, it knows that $1 is the first argument. So these are ordered. So here we're going to print character, word, and line count in this file. Word count returns the character. C-W gives you the word, and -L counts the number of lines. Cut will split the output on the spaces, and then we'll print the first field. So you should get this kind of output here on the right. I'm going to go through these quickly because I know we need to wrap up. This one will take arguments, except we'll redirect the input by passing the name of the file. So here we have .counter file1.txt, and here we also looked at the name of the file1.txt, looking at that as input. And the same kind of syntax where we're looking at the number of characters, words, and lines. Conditional statements. If some test is true, then do some activity. If the test is true, then do some actions, or else statements. So this is an if-else-if kind of statement. So it works just like it would work in normal programming. So here are several examples of conditional statements. And so comparing values, $1 less than $2. Here, $1 less than or equal to is $1 greater than or equal to. So here we'll do number comparison, the numbers 2 and 2, 2 and 3, 3 and 2, 3, 1, 2. And then you can also compare strings. So using lexicographical ASCII order. So integer literals are treated as strings in this context. So you're still doing a comparison of two strings, but it's using ASCII compare. So ABC is not equal to DEF. DEF is not equal to ABC, but ABC is equal to ABC. Excuse me. You can use this for testing for a file existing. This is really handy if you're in a big bash script trying to running an application, and when it's done you want to make sure your output is directed somewhere where you want your output to go. You can test to see if the file is there. You can use this for file management. So if the file exists, then you can echo the kind of file. Is it a regular file? Is it a directory? It's not. And then if not, then if it doesn't find the file, then it doesn't exist. All right, so in summary, using Linux skills, it'll help you become a more effective user and allow you to look at what's happening, follow your processes, manage your data, develop scripts that help you analyze your data or run your jobs. And then we've covered most of what we think you should need to know, but if there's something missing, let us know. But also, you can go deeper to other batch scripting tutorials, for bash scripting tutorials, and other forums and tutorials. And with that, I'm done. I'll stop sharing. Thank you for your time, and it looked like there were questions. And